Today we will be presenting about nuclear fission as sustainable energy sources.
What is nuclear fusion? Nuclear fusion is the process where two atomic nuclei collide and combine to form a single heavier nucleus while release a massive amount of energy. The reaction takes place in a state called plasma, such as sun along with all other stars. In example, to fuse inside the sun, atomic nuclei must crash into each other at incredibly high temperature. This extreme heat gives them speed and energy they need to break through their natural electrical force, which would otherwise push them apart. Why we choose this topic is chosen because it sits at the heart of modern physics by combining quantum mechanics, plasma physics and nuclear theory in one subject. It is actively developing with real breakthrough happening now. Other than that, it also relevant because it applies its most fundamental concept in one place like quantum tunneling, plasma behavior, mass energy equivalence, and electromagnetism all play essential roles in making fusion work.
To gather information for our topic, we use several independent learning methods. First, we conduct online research using trusted educational and scientific websites to obtain recent information and development in nuclear fusion technology. Next, we perform a literature review by referring to modern physics textbooks, scientific journals, and research articles related to nuclear fusion. These sources help us understand the fundamental concept, principle, and current progress in fusion energy research. Finally, we carry out an information comparison by comparing data and finding from multiple sources. This allows us to verify the accuracy and reliability of the information and gain a broader perspective on the benefits and challenges of nuclear fusion. By using a variety of relevant and credible sources, we ensure that the information presented is accurate and appropriate to the scope of modern physics. During our independent learning process, we encountered several challenges while researching nuclear fusion as a sustainable energy source. The first challenge was understanding complex scientific concepts such as fusion reaction and the conditions required to achieve fusion. To overcome this, we refer to simpler educational resources, explanatory videos, and introductory materials before exploring more advanced sources. The second challenge was finding reliable and up-to-date information, as fusion technology is a rapidly developing field. We address this by using reputable scientific journals, research papers, and trusted websites from recognized scientific organizations. The third challenge was managing the large amount of information available. Since many sources discuss similar topics with varying levels of detail, we selected the most relevant information and cross-checked multiple sources to ensure accuracy and consistency. By overcoming these challenges, we were able to develop a clearer understanding of nuclear fusion and present accurate and reliable information in this project.
Next, this slide explains about the basic concept, theories, and laws behind nuclear fusion. First, nuclear fusion is the process where two light atomic nuclei combine to form a heavier nucleus, releasing a large amount of energy. This reaction occurs in a plasma state, which is an extremely hot and charged gas made up of ion and free electron. Next, the theory of the nuclear fusion explains that fusion can only occur under extremely high temperature and pressure. This condition allows the nuclei to move close enough for the strong nuclear force to overcome the repulsive force between them. Fusion energy is produced because a small amount of mass is converted into energy. According to Einstein's equation, E equals to mc squared. The most commonly used fusion fuels are deuterium and tritium. When they fuse, they produce helium and neutron and release about 70.6 MeV of energy. Finally, the main physical law involved are instant mass energy equivalence law and Coulomb repulsion. Since atomic nuclei are positively charged, they naturally repel each other. Therefore, extremely high temperatures are needed to give the nuclei enough energy to collide and undergo fusion. Magnetic confinement fusion, or MCR, use powerful magnetic fields to confine extremely hot plasma inside a toroidal donut-shaped chamber. Strong 13 Tesla magnet prevent the plasma from touching the reactor walls, while neutral beam injection add high energy particles to further heat the plasma. Water circulating around the reactor cools the structure and capture the heat produced, which then converted into steam to drive turbine and generate electricity. Then, the tokamak is the most widely used type of MCF reactor. It uses a donut-shaped chamber and strong magnetic fields to contain plasma at temperature above 100 million Celsius. At this extreme temperature, hydrogen isotope gain enough energy to overcome repulsive force and fuse, releasing a large amount of energy. Next, we will talk about inertial confinement fusion. Inertial confinement fusion (ICF) use powerful energy beams to compress and heat a small fuel capsule containing deuterium DT fuel. There are two main methods: direct drive, where laser hit the capsule directly, and indirect drive, where the laser first strike a gold cylinder holarium to produce X-ray that compress the capsule evenly. The rapid compression creates extremely high density and a temperature above 100 million Celsius, allowing the DT nuclei to fuse and release a large amount of energy. The reactor then captures this energy using cooling system that absorb the heat and convert it into steam to drive turbine and generate electricity.
Now let's take a look at applicability in daily life. First, nuclear fusion is an advanced energy technology that aims to replicate the process that powers the sun. In fusion, light nucleus such as deuterium and tritium combine to form helium, releasing a large amount of energy based on Einstein's equation. Although fusion is still under development, it has the potential to provide clean, sustainable, and low-carbon electricity. In the future, fusion energy could power homes, hospitals, transportation systems, and industry while reducing greenhouse gas emissions and dependence on fossil fuels. Therefore, fusion energy could play an important role in creating a cleaner and more sustainable world. Now let's discuss about recent study on nuclear fusion. Recent developments in nuclear fusion have brought scientists closer to achieving practical fusion energy. Fusion has the potential to provide a nearly limitless, sustainable, and zero-carbon source of electricity. The ITER project in France is developing a large tokamak reactor that uses strong magnetic field to contain high-temperature plasma. Meanwhile, researchers at National Ignition Facility in the United States achieved fusion ignition, where fusion reaction generated more energy than the laser energy absorbed by the fuel. Since fusion mimics the process that powers the sun, these breakthroughs are important steps toward making fusion viable energy source for the future. Let us jump to potential career related to nuclear fusion. Nuclear fusion creates many career opportunities for students interested in science and technology. Nuclear physicists study nuclear reactions and energy production, while plasma physicists investigate the behavior of plasma under extreme conditions. In 2026, AI is also becoming an important tool in fusion research, helping scientists predict plasma instabilities and improve reactor performance. This career requires strong analytic thinking, problem-solving skills, computer programming, and knowledge of physics. As global investment in fusion energy increases, the demand for skilled professionals in fields is expected to continue growing.
To succeed in these roles, we need a strategic plan. For essential skill, hard skill like proficiency in scientific programs such as Python or MATLAB are crucial for running complex plasma simulation. Equally important are soft skills, specifically cross-cultural communication for international teamwork. To gain the required experience, we must actively participate in laboratory, research, and secure industrial internship. Most importantly, we have established clear career goals. Our short-term goals over the next 2 years is to excel in foundational physics and master data analysis tool. Our medium-term goal is to secure a relevant physics degree and an undergraduate research internship. Finally, our long-term goal is to complete a PhD and contribute to global research facilities. Next, we must understand the significance of continuous self-development. Nuclear fusion is a fast-paced field, and technologies update rapidly. For instance, researchers are now integrating artificial intelligence to help stabilize plasma. If we don't continuously educate ourselves, our skills will become outdated. By constantly reading high-impact scientific journals and attending global conferences, we not only track international milestones but also expands our professional networks. which is vital for global collaboration. Finally, we must prepare for career challenges. The first major challenge is the lack of local facilities. Advanced fusion reactors are incredibly expensive to build, meaning we don't have them here in Malaysia. Our strategy is to overcome this by focusing on theoretical computer-based simulation research and actively apply for international scholarship to study abroad. The second challenge is the sheer technical complexity of containing superheated plasma. We can overcome this through cross-disciplinary collaboration by teaming up with computer scientists and materials engineers to solve these complex scientific problems together. This concludes our career development plan.